We're working on Unit 6, Lesson 4, which is from Section 8.5, Exponential and Log Equations. Today, now we're going to talk about the log equations. So the assignment, I believe, starts on 472. It might be 473, but you're doing 33 to 47 odd, and then 64 and 83. So let's flip to the back. So we're looking at the opposite type of equation now, meaning we're looking at log equations. And so we'll want to use exponentials to solve log equations the same way that we use logs to solve exponentials. So for our first problem, we've got 2 log of 3x plus 1 equals 10. Okay, so we want to isolate the log so that we can switch it to exponential form. So for the second problem, notice that the log's already by itself. We have the thing that we're taking log of. And so in problem A, we have this 2 in front. So we know that with properties of logs, we could use power property and move that to be squared. But it's better if we just divide by 2. So if we just divide this by 2, that's going to kind of simplify the work. So that gives us log of 3x plus 1 equals 5. Okay. And so the big idea here is that we want to switch it to exponential form. So what we need to know is we need to know the base of the log. Remember that if there's no base showing, it's really a base of 10. Okay. So we're going to rewrite this as a base of 10 raised to the 5th power is equal to 3x plus 1. Okay, so we've got 10 to the 5th equals 3x plus 1, which is equivalent to log base 10 of 3x plus 1 equals 5. And so now we have a problem that we can solve. So let's simplify 10 to the 5th. Remember that 10 to any power is just a 1 with that many zeros. So we've got 1, 2, 3, 4, 5 zeros. So that's actually 100,000. Okay. So 100,000 equals 3x plus 1. So we want to get x by itself, which means we want to move the 1 and 3 over. So let's subtract 1 from both sides. So if I have 100,000 and I subtract 1, that means I have 99,999 left over is going to be equal to 3x. So now to get x by itself, I'm going to divide both sides by 3. This is just a bunch of 9s. And so think about 9 divided by 3 is 3. So I'm just going to have as many 3s as I do 9. So it's going to be 33,333 as our answer. Okay, so we're switching to exponential form. Then we just have something we're evaluating and solving for x. Okay, so if we look at B, our log's already isolated. We don't have to divide by anything. So if we go ahead and switch it to exponential form, it's a common log again. So our base is 10. So we're doing 10 raised to the 4th power equals our 2x minus 2. So 10 to the 4th power equals 2x minus 2. So we can evaluate 10 to the 4th. So that gives us 4 zeros behind our 1. So that's 10,000 equals 2x minus 2. So to solve for x, we're going to add 2 to both sides, which gives us 10,002 equals 2x. And then we want to divide both sides by 2. And so x equals 10,000 divided by 2 is 5,001. Okay, so this is when we have a single log and it's equal to some kind of number or expression or whatever. Okay, so when we have that, that's our process. When we have multiple logs, we actually want to condense before we do this to solve, okay? So what we're looking at here is we actually have logs on both sides, okay? And so what we want to do is condense our logs first, meaning if I'm subtracting logs, I turn it into division. if I'm adding logs, I turn it into multiplication. Okay, so this minus tells us we're going to make it into a quotient. We're going to use our quotient property. When I have a sum like this, that tells us we're going to use our product property. So meaning I'm going to rewrite log base 6 of x plus 1 minus log base 6 of x as a single logarithm. Because this is subtraction, that tells me that I'm dividing my two pieces that I'm taking log of. So the first part inside the log is the x plus 1. So that's going on top because it's positive here. And then the other one is x, and that's going on the bottom because it's negative there. Okay. And so this is going to be equal to log base 6 of 29. So when I have a log equal to a log, what we learned when we talked about exponentials, I'm going to back up a little bit, is that if I have a log equal to a log, so I'm looking over here at these guys. So if I have a log of n equal to log of m, which is essentially what I have right now, that's equivalent to m just equaling n. Okay. So what this means is that I can ignore the logs and just use the values that I'm taking the log of. Okay, so let's look at that this way. So I can now ignore the logs, is what this property says, and rewrite this without them. So I can ignore the logs because they're the same. Let me write this better. Hold on. So since I have both sides have a single log with the same base, that's why I can ignore the logs. Okay. So the important part is that they have to be the exact same log, and it has to be by themselves. So notice that I couldn't ignore them when I started. I couldn't just say, oh, they're all log base 6s, so let's throw them out. I have to have the exact same log, and it has to be by itself, so one on each side. So I have to condense before I can do anything. So I'm ignoring the logs. So I have my x plus 1 over my x equals 29. And so when I have a fraction like this and I want to solve for x, remember that I need to think about it as being able to cross multiply. Okay, so I want to put the 29 over 1, and then I'm going to multiply 1 times x plus 1, which isn't really going to change anything. So I've got 1 times x plus 1 equal to, and then I want to multiply the x times the 29, so that equals x times 29, or 29 times x. So really I just have x plus 1, because if I distribute the 1, that doesn't change anything, equals 29x. So I'm solving for x here, which means that I want all the x's on the same side. So since their 1 is already over here, I have to move this x over to be with the 29. So if I'm taking an x away from here, I'm left with 1. I have 29 x's and I'm taking 1 away, I'm left with 28. So this tells us that 1 equals 28x. So to get x by itself, we're going to divide both sides by 28. So this problem tells us that x equals 1 over 28. Okay. So again, big idea is condense so that we can ignore our logs. So we already said that we're going to use the product property for this one because we're adding our logs together. So we have a log base 5 now. So log base 5, and we're multiplying because we have addition. So we said, okay, we see that we are adding, so that means that we're actually multiplying here. And so when I multiply this, I'm multiplying 6 times my 2x squared. So I'm going to take a second to kind of simplify this. The other one I couldn't simplify because it was just x plus 1 over x. So I've got log base 5, and 6 times 2x squared is 12x squared equals log base 5 of 48. Okay. And so this is the point where I can now ignore my logs. So I got my 12x squared must be equal to 48 because it's the same log on both sides, right? So the only way that's equivalent is if those two things are equal. So to get x by itself, we have to divide by 12. So x squared equals 48 divided by 12 is 4. And then we need to take the square root of both sides to get rid of x squared, or the square. So if I take the square root of x squared, that's x. Because it's an even root, we have to write plus or minus, because remember that positive 2 squared is 4, but negative 2 squared is also 4. Okay, so whenever we take that even root, we have to write plus or minus because it cancels out that negative. So we saw two things today. We saw a log equation where I have a log and a number. And so within that, I want to switch it to exponential form and be able to solve for my variable. We also saw logs equal to logs where there's more than one log on one side, where we had to either use quotient property or product property to condense those. And then we were able to ignore the logs. Know that you might see a problem where you have something that's a hybrid of the two. So you might have to add or subtract two logs together and then switch it to exponential form, okay? So that's all for this lesson.